Hi, my name is Minky Zhang, and I recently gave a workshop at the AI Engineer Summit in New York City. There was significant interest from CTOs and engineers who are working really hard to build LLM workflows. And I'm recording this video because I didn't have enough time to cover everything I had prepared for the workshop. I hope you'll find my workshop valuable. If you're interested in continuing the discussion, please check out the link in the first comment. To say a little bit about myself, I studied physics and philosophy in university. So I really like to think about problems from a first principles point of view. And you might see that way of thinking in this workshop as well. I'm originally from South Korea and immigrated to Canada in 2021. Since then, I've been working as a full stack engineer. But over the last year and a half, I've been deeply immersed into the AI space, building a lot of LLM applications. And I found flow engineering to be something essential when it comes to building these AI applications. But I realized that there are many resources to learn from. Through my project, I've gained some insight on flow engineering through trial and error, and I'm really excited to share that with you today. So, what exactly is flow engineering? This term was coined by Andrej Karpathy about a year ago when he read about Arpacodium, which has a novel approach to code generation. Basically, instead of calling LLM just once, Arpacodium calls LLM many times in predefined steps. And here's what it actually looks like. First, the LLM is prompted to reflect on its given problem and task. Based on its reflections, the LLM will proceed to generate possible solutions. So, as you can see, it has already undertaken two steps before generating the solution. And this is not the end. From here, the LLM ranks its possible solutions and generates its own tests, running the tests against the solution. With these added steps, Arpacodium managed to improve the accuracy of code generation by a great deal. Seeing this process, Andrej Karpathy said, hey, maybe we could call this flow engineering. So one way to think about flow engineering is breaking down of complex tasks into predefined steps. And you might want to hold on this idea of predefined steps. It's important because it distinguishes flow engineering from autonomous agent. As some of you may already know, and Anthropic recently released an amazing blog post called Effective Agent, autonomous agent also break down a task into multiple steps. However, these steps are not predefined by the engineers, but generated by the LLM itself on the fly. By this point, you might be thinking, flow engineering is about simply designing the steps, designing the edges and nodes. But I'm going to make a point here. From my experience of building LLM applications, flow engineering was more than just designing workflows. And to really understand this, I'd like to zoom out a bit and consider a larger historical context, especially the Industrial Revolution. Because I believe you can think of flow engineering as the industrialization of knowledge work. And of course, we can learn many lessons by looking back into the history. So, before 1904, automobiles were produced using a craftsmanship approach. Skilled workers built each car by hand, carefully assembling and fitting parts with great attention to detail. And this method allowed for high quality and customizable vehicles. But it was extremely slow and costly. In fact, it took about 12 hours to produce just one car, and it cost about $2,000 to $3,000 at the time. But Henry Ford revolutionized the industry by introducing the mass production system. Instead of having one worker build an entire car from start to finish, he used an assembly line where partially assembled cars move from one worker to the next, with each person focusing on a single step in the process. This dramatically increased the efficiency, reducing production time to just 1.5 hours. And the cost was only $260. And here's a question for you. How many distinct motions do you think it takes to make a Model T, the first model from Ford? Believe it or not, it took 7,882 motions. It wasn't the case that manufacturing car was insanely difficult. At the time, cars weren't that sophisticated. But it was the case that Ford was widely obsessed with maximizing the efficiency of the process. In fact, a friend of Ford recollected him tiptoeing and dancing around the factory floor, constantly thinking, what could we do here? What could we change the production process to yield more cars faster? And his obsession with optimization carried over into workstation design. In this picture, a young man is trimming a wooden wheel frame for the vehicles. The workstation is designed so that all unnecessary human motions are eliminated. Material and tools were all in easy reach of the worker, and after he finished his job, he simply slides it down to the next worker. And if you look closely at the wooden frame, you'll notice small holes in it. The worker has to simply place the frame on the bench and align the holes with the pegs that are positioned at just the right spot to cut the frame precisely. There was no time wasted with measuring or marking where to cut. I like to think of this as the skill being built into the tool. The craftsmanship is in the workbench itself, not the training of the worker. So Ford didn't require any skills for the workers. Skill was actually engineered out of it and embedded into the workbench. Even mistakes could be accounted for. This wooden bar on the slide is acting as a guardrail. This means that if the frame is higher than the bar because the worker just forgot to cut one side, the guardrail would stop it from sliding down to the next worker. And this is not the end of Ford's relentless optimization. Ford changed the specification of the final product to make the factory more efficient. He famously said, any customer can have a car painted any color they want as long as it is black. He took this risk because having many colors of cars will make the process more complicated. So, we have 4 takeaways from Ford's success. 1. He was obsessed with decomposing tasks. 2. He designed an efficient work environment. 3. He embedded skills into the workbench. And lastly, he modified the final outcome. I want you to keep this in the back of your mind because it will be highly relevant to flow engineering. Now, let's skip forward in time. During World War I and II, mass production got even more sophisticated and scaled up. This is a picture of Bell Aircraft Corporation in 1944. They were creating airplanes in the same manner of mass production as Ford. In the 21st century, robots appeared. Now, almost everything that humans used to do is automated by these robots. But these are all about physical labor. Today, we're talking about LLM workflow, which is more about cognitive tasks. It might therefore be insightful to take a look at the history of industrialization within knowledge work. Let's start from the librarians in the medieval age. Librarians at the time were tasked with tracking all the books. They had to know where any book was. They had to know what contents the book included so that when scholars or priests visited the library, they could find just the book they needed. To optimize the work, they did have some categorization system, or they had a ledger that keeps track of their books. But mostly, the librarians relied on their memory. And this job was handed down through apprenticeship. The only way to be a librarian was to learn under a master and memorize all the knowledge in their brain. Obviously, this cannot scale up. The modern library, however, did manage to scale up. Since available information in the modern day is too vast, it cannot fit into a single brain. Before computers, librarians, as though you see on the left from 1937, had to find a way to adapt. They created a highly systematic way to categorize and index information for easy retrieval, such as the Dewey Decimal Classification you see on the right. With such systems, librarians processed all information by hand manually. Call centers are another great example to see how humans industrialize knowledge work. As you can see in the diagram, call centers have an organization hierarchy consisted of a supervisor, senior agent, and regular agent. When you call, you get to talk to an agent at the bottom rung of the hierarchy. And if the issue is within their scope, they handle it right away. But if it isn't, they will pass it over to a senior agent who is experienced and authorized to handle more intricate tasks. The reason that call center limit authorization to its bottommost agent is twofold. First, it's too costly to educate all the agent on every single issue that could arise with customers. Second, the corporation needed to standardize the process so that customer can have consistent services. Most of the agents are taught only to follow a decision tree, which helps them navigate any call with a customer. In other words, they ask a scripted question and input the customer's answer into the decision tree, which in turn provides them with the next step. We can draw a connection between a call center decision tree and Ford's workbench. As Ford engineered out skill from workers and embedded into the workbench, call centers engineered out judgment from an agent and embedded into the process. There is, however, one important difference between industrializing physical labor and knowledge work. Knowledge work becomes counterproductive when it gets broken down too much. This is because communication between workers takes time and effort. And here's what I mean. Let's say you call a call center and spoke to a single agent. The agent would reliably assist you from one step to the next with a coherent memory of your conversation. On the other hand, let's say you call a call center and had to be assisted by multiple agents in sequence. It's probably not going to go as smoothly as the first call center with a single agent. For example, some information you've already passed on to the first agent might not have been delivered to the second, or it might have been inaccurately delivered. Thinking from agent side, things are not that much better. As an agent, you're expected to summarize your interaction with the customer in order to pass it over to the next agent. On top of that, you have to read the summary of the previous agent thoroughly. The whole process is simply time-consuming and error-prone. In physical labor, we didn't have to worry about this because the workers are passing physical objects that have a traceable progress. Moreover, physical labors are mostly assembling or adding some material in a straightforward order. In knowledge work, on the other hand, workers are passing information or memory, which is not easily transferable. It takes extra time and effort to do it right. And oftentimes, the steps you need to go through are not in a straightforward order. So when you break things down for knowledge work, there is an optimal level of task decomposition. Okay, so we had craftsmanship to mass production to robotics, library apprenticeship to call center agent, and yes, we have LLMs, the transformer architecture. In the historical context of industrialization, LLM is kind of equivalent to robot in knowledge work. It has the potential to automate the job of knowledge workers. But here's the catch. Unlike robots, which is effectively identical to human motions, LLMs are not identical to human intelligence. First of all, LLMs are stateless. Whenever you make an LLM call, you're calling a brand new LLM that doesn't have a memory of what you've said so far. It's your job to manage chat history or some sort of summary of the process and put it into a prompt every time. As a result, a task for LLMs is always already decomposed into more tiny parts than it can be done for human tasks. But luckily, LLMs makes up for their deficiency by being faster and less lossy than humans when transferring information. And reasoning models are expanding this horizon as well. The second limitation of LLM is that LLMs don't complain about errors in the process. Humans can ask questions to managers if the instructions are not clear. LLMs just try their best to guess even though the prompt doesn't make sense to them. Therefore, it's the engineer's role to inspect and address errors. Lastly, we can't expect LLMs to make good judgment off the shelf. We saw this in the call center scenario. The entry-level agents are not expected to make good judgment because it costs too much to train them. Similarly, we can fine-tune LLMs to align them to specific tasks, but it comes with costs and some drawbacks. Like decision tree were introduced in call centers, we need to embed judgment into the workflow. Bearing this limitation in mind, we can think of flow engineering as designing and optimizing cognitive factory. And the following can be read as a job description of flow engineering. First, flow engineering involves decomposing complex tasks into optimal level. The tasks cannot be too fine-grained, nor can they be too coarse-grained. Second, flow engineering involves designing ergonomic prompts for LLMs. Like Ford meticulously designed the workbench to eliminate unnecessary motions, we need to refine prompt so that they become easier for LLMs to understand. This includes refining variable names and tool descriptions and so on. So you can guess how much prompt engineering this would require. Third, flow engineering involves designing communication between LLMs. For example, you have to manage information so that it is stored, updated, and curated appropriately. We'll go deeper into this in the workshop soon. 4. Flow engineering involves embedding judgment into the workflow. Like call center agent follow a decision tree, we should create some kind of robust rules that LLMs can reliably follow. This is especially important for conditional edges, where LLMs decide which node it should proceed toward. As for number 5, flow engineering involves overseeing LLM calls and improving them iteratively. We saw Ford tiptoeing around the factory floor intent on optimizing the factory line. Similarly, we have to close read prompts and responses from LLMs to find errors and increase efficiency. Moreover, we have to evaluate the performance of each LLM call with well-designed dataset. And number 6, we have empowering LLMs with proper tools and access to resources. Like humans, LLMs can't do that much without proper tools or access to resources. Finally, flow engineering involves tweaking the specification of the final output in order to simplify the process. If you recall, Ford audaciously restricted the color of his cars to black. Sometimes, flow engineers also need to make that bold move. As you can see, there are many components that you have to consider when designing and optimizing cognitive factories. Okay, so we have the job description of flow engineering, and you might ask, how to be better at this? Personally, I like to think that being good at flow engineering is a matter of attitude and principle more than following certain rules. This is because hard and fast rules are not exhaustive. There will be situations that the rules fail to cover. Moreover, they are often too rigid to guide us in the complex real-world problems. In the world of software engineering, there is the Agile manifesto, which delineates a set of values and principles designed to improve software development. So, what would an Agile manifesto for flow engineering look like? After the workshop, I'm going to propose a draft manifesto for flow engineering. And I hope this generates more discussions and we can collectively improve that manifesto further. Okay, so let's get started with the workshop. This was originally planned for in-person activity, but since I'm recording this video, you can follow it on your own, or you can just watch how it goes. So we're going to industrialize the trip planning process. So I created an app, and we're going to come up with the workflow for that app. We're going to have trip information input from the clients, and we're going to generate this trip itinerary, which is basically a list of dictionary that has title, location, description, time, and so on. There are parameters for this workshop. First, we're not going to handle bookings. The booking is another topic that requires another workshop. It's an interesting topic, but we're not going to cover that. We're going to only plan the trip schedule. We're going to restrict communication with client to only the initial survey. So once the client submit this form, we're not going to ask the user any preferences or the user cannot give feedback to the final outcome. So this is just for simplicity. We're going to only use Perplexity and Google Maps for web search because search is another interesting topic that requires another workshop. We're going to use LangChain ecosystem, especially LangGraph. But even if you're not familiar with that, don't worry about it because we're going to talk at a high level. Okay, we're going to have 7 steps, and I found having this step before actually building the workflow or working on actually code the workflow is very helpful because you can anticipate what steps you need, what process you need, what tools you need in advance just by having 1-hour session. So I'll walk you guys through how the step goes with an example. So first step is simulate the planning process on our own. Ideally, we'll make groups of 2, and person A in the group will plan the trip thinking out loud. And person B is going to document person A's reasoning process. And once they're done, they're going to create how-to steps together. And how-to step looks like this. So this is an example for how to write an essay. To write an essay, you first understand the topic and requirement, then research and create a thesis statement, and then outline the essay, write the essay, and revise and edit. So these are well-defined, well-ordered how-to steps that anyone can follow this step and write an essay, right? So in this workshop, we're going to actually create how to trip a plan. But since this is not an in-person activity, I'll just use this example to demonstrate how these 7 steps goes. So this is the trip information that you can use if you want to do it as an activity. You can use this one. And the second step is you're gonna at this point you're gonna have how to steps for your problem. This step you have to test it. So rigidly follow the steps and see if you can actually accomplish the goal. This helps you to detect some missing steps or some assumptions and so on. The next step is decompose overloaded steps. And by overloaded, what I mean is those steps that contains multiple decision points and substeps. So let's take a look at the example. So in the how to write an essay, what steps are overloaded? There are many, but I'll give you 2 examples. First, choose a topic. So when humans choose a topic for an essay, you don't choose it right off the bat, right? You first kind of brainstorm it and create some list of possible topics, and you choose one out of it, right? So I've broken it down into two steps: brainstorm possible topics and choose one topic. And second example is research. So this is very hard, actually very hard and hard to decompose step. But here's an example. This is not ideal, but here's an example. So for research, you look up the topic on Wikipedia and read it thoroughly. And create 3 questions based on what you didn't understand while reading the Wikipedia page. And look up the question and repeat step 4 until you're confident. So this is one way to do research. Humans do research more orderly and intuitively, but at the end of the day, we have to delegate this task to LLMs. So you have to make these steps well defined and well ordered. Once you decomposed the overloaded steps, the next step is embed judgment into flow. And here's an example. Choose one topic. This step requires judgment, right? When you're choosing one topic for an essay, you might use your preference, you might use some requirement, you have to make some judgment. Humans do it quite intuitively, but we have to embed the judgment into flow. And here's how you can do it. Evaluate each candidate against the following criteria. First, the topic should not be too esoteric. Second, the topic should not be too outdated. So these are arbitrary criteria that just come up with, but you get the point, right? And importantly, criteria is better when it has objective marker. For example, so if you just gave the topic should not be too esoteric, that sentence to the LLM, or even a human, I would ask, what do you mean by too esoteric? Does it mean that everyone in my classroom should know the topic, or 90%? What do you mean by esoteric, right? So criteria can have these concepts that are too qualitative and not quantitative. And if you want to improve that, if you want to have some steerability, it's better to give them more specific information, more specific marker. So here I did like this. 90% of grade 11 students in the United States should be aware of it. The topic should cover events that happened within the last 5 years. Don't get me wrong, LLMs would not use these objective markers for research or some kind of agentic actions. For example, when you say the topic should cover something that happened in the last 5 years, LLMs would not think, okay, today is this and 5 years ago is this. Did the event happen during this time? Right? The LLMs don't know even what today is, right? But so these objective markers are just making your subjective criteria more objective, and also gives you kind of a knob that you can tweak. So when LLM only picks really, really recent topics, you can increase the number of years of this criteria. Step 5, embed working memory into flow. LLMs are stateless. It's your job to manage state or some kind of working memory to give them context. And we have very intuitive working memory, so we often forget this limitation. And one way to do it intuitively is that imagining you're suffering from short-term memory loss and memory resets every step. Okay, so look at this example steps. What steps do you think need help when you have these conditions? It's actually every step, right? For example, when you brainstorm possible topics and you move on to the next step, you forget what you brainstormed, right? You have to keep all the possible topics in memory. And when you do research, you have to remember what you researched. So one way to do that is whenever you do research, you summarize what I've learned. And in order to do it, you need to have some artificial working memory. And here we have two working memory variables. So this is a state variables, and we have topic and summary of readings. And topic is list of strings. So when you brainstorm possible topics, you add those topics into this list. And then when you choose one topic, get rid of everything except the one that you chose. For summary of reading, you just append new summary into this list. Step 6, parallelize if applicable. So this is a simple step. Just read your steps and figure out which steps can be benefit by parallelizing them. And it's not only the step, a single step that can be parallelizable, but also whole process. So instead of having one process, you can have multiple process going at the same time if those processes don't need context from each other. I'll show you how I did in my workflow example soon. Okay, so this is a final step. Identify which steps really require LLMs. LLMs are great technology, but it doesn't mean that we have to use them for all kind of tasks. Some tasks that don't need intelligence can be hard-coded with traditional programming language. Okay, so that was the 7 steps that I prepared, but I want to add one more checklist. First, check if all the tools and resources for the workflow are available. So, for example, if you have to access to internal data set for your organization, you need to have a pipeline. You need to have an API. You can access the data. If you don't have the pipeline yet, you may build them first. Second, check if the task requires high flexibility. For example, we looked at an example how to write an essay, and we've broken down research step into 3 sub steps. Read Wikipedia, come up with 3 questions, and look up those questions and repeat that until you feel confident. But this is very rigid way to do research. Sometimes you have to go deeper, you have to search many different ways, you have to navigate the website, and so on. If your task require high flexibility, you may find end-to-end reinforcement learning more effective. But this requires you to collect data set to train the model, and you have to have a suite of machine learning engineers. So it's up to you. Either confine the task so you can sacrifice the flexibility and use the LLM workflow. Or if you want to really achieve that high flexibility, you have to consider end-to-end RL. Lastly, check if the task needs a deep synthesis of information. LLM workflow, the way it processes information is very segmented. And this segmented workflow is not perfect for tasks that require holistic view. For example, scientific discovery. This requires you to read a lot of papers, do a lot of work, experiment, and have all the knowledge in your brain. And you process it unconsciously and come up with creative ideas or good understanding about that science. So if you're trying to tackle those tasks that requires tens of years even for humans, you should reconsider your problem and make it more easier. Okay, now I would like to share my workflow for this trip planning application. And I want to emphasize that this is not the only solution. I've built this in a week for this workshop, and I had to sacrifice some complexity. So even if you don't agree with the workflow, bear with me because I'll focus on actual implementation, which can be applied to any kind of workflow. I have 2 processes going on at the same time. One is on top and one is at the bottom. So I'll explain the top first. So this one, add terminal schedule, is blue, which means it's hard-coded process. It doesn't, I'm not using LLM in this node. So what this doing is the user is going to input their terminal schedules, like when they arrive to the airport, when is their departure time. So with that, I'm creating terminal schedule and add it into the trip schedule. So it will look like this. So trip schedule timetable. This is one of my state variables. And basically, throughout the whole workflow, my goal is to fill out this schedule timetable. And in this step, add terminal schedule, I simply add these two items. And here I'm adding terminal to accommodation transport schedule items. So I'm assuming that when you arrive to the terminal, when you landed on that city, you're going to go to the accommodation and check in. And when you're leaving, you're going to leave from the accommodation. So this is just simplification. So this would look like this. So I added transportation from terminal to accommodation from accommodation to terminal. So this was the this step, and in parallel, I'm doing the same another process, which is filling other schedule items. So here, I first calculate total trip free time, and this is also hard-coded process. I'm just getting all the schedule information and just calculate total free time. And why do I do that? I do that because I want to do internet search. I want to create n number of internet search queries based on the trip free time. So if the user is going to stay in the user's trip is longer, then I want to generate more search queries because I would need more information to fill in that long schedule. But on the other hand, the trip is just 1 day, then I might be enough with 3 search queries. So that's how I'm deciding how much I should research. Again, this has limitation, but this just makes it simple. Once I have the trip for time, I generate search queries with this reflection loop. And I have this reflection loop here, here, and here. And you can think of this as actually autonomous agent within the workflow. So we have very rigid workflow, right? But we also have some autonomous process here because LLM can decide, oh, I generated enough queries, now I can move on to the next step. But importantly, I have max iteration count. So this loop cannot go forever. It should stop at some point, but it also can be terminated by the LLM. So once we generated all the search queries, I do internet search in parallel. And when we get all the internet research, we start filling schedule items. And here I'm filling schedules in an incremental manner. So I'll show you how it works with my app. So this is the app that I built. The user has the trip information input form, and they can add like what kind of theme the trip they should be, also their budget, where they're visiting, and so on. And with this information, you can generate the trip using that workflow that we solved just now. So when you start, you can see what's going on under the workflow. It first calculated 3 hours, it was 17. I'm just saying 1 day. It added terminal schedule, which is this. It generated queries for internet search. Oh, it generated 2 because the trip is short. And these are the queries that it's going to be used as a search. So it said free or cheap because I said budget friendly, and landmark architecture because I said I like architecture. Okay, so it started internet search in parallel. We can see all this process in real time. Yeah, and then also it added this terminal accommodation schedule. okay, the internet search is done. So it has summarized internet search result. And with this result, it start filling schedule items. So we have only 2 schedule items here, but it's going to add more schedule items in this list. Okay, it just added 3 schedules. So go to accommodation and have dinner at Joe's Pizza, have a jazz gig at Village Vanguard, and go back to the host your accommodation. So it adds schedule um, about 3 to 4 schedules at one time and do reflection and check if there is missing things. So actually here it made some mistake because, oh yeah, so it made a mistake when we went to the accommodation at 5:30. We have dinner at 6, but there was no transport item. So it reflected its own schedule items that it generated, and it detected, oh, there is a missing transport schedule. Let's add it. So it added that. And here we didn't have this one, right? From here to Greenwich Village, it took it said it actually added a new tour schedule, walk and enjoy the village. Yeah, that's basically the app. So after internet search, we do this fill schedule item, which is filling schedule like 3 to 4 schedules at once and reflect. And once all the schedules are filled, then we do another validation session. You can remove this, but if you want to increase the performance, then you can add this kind of validation reflection steps. Okay, let's look at the code. Before diving into the code, I want to make sure that we're not going to talk about a LangGraph. So this is not a LangGraph tutorial. LangGraph team has an amazing tutorial. Please check that out. But I'm only going to focus on the thing that I really want to emphasize. So we're going to start from state. As I said, LLMs are stateless. And in this workflow, it's your job to manage the state, the memory. And I divided the memory in two categories. First is input state, and second is overall state. And overall state is inherited from input state. So input state is something that you need when you initiate this workflow, and you're not going to change it along the process. So username, it's not going to be changed. Trip arrival time, all this trip information, it's not going to change, right? So it's better to separate this into different states so that you can manage it better. In overall state, these are all going to be updated during the workflow. So trip free hours, as I said, I'm going to calculate it with Python code. It will just update this number. An internet search result list is simply a list of dictionary that contains the search result from Perplexity. And I want to explain the reducer function here. In LangGraph, if you wrap your type with this annotated and have this reducer function, the LangGraph is going to use this function to update the state. So here, let's look at this. Extend is a very simple reducer function. It's basically extending the original list with new list. So whenever you have a new search result, you're just going to extend that into this state variable. And I have a special rule because sometimes I have to reset the search result. So I can have this kind of handy rule. Okay, so the most important state variable is schedule list. So if you think about Ford's assembly line, this is the partially assembled car that moves around, moves through the assembly line. Okay, so basically what we're doing is we're creating this list of schedules and we're incrementally adding things or modifying, removing things from this list. And this list is has the type of list, and each schedule item is this schedule item. Let's look at that. So I'm using PyIdentic model to define schedule item. It has ID, activity time, location, title, the description, and suggestion. So I'm using this PyIdentic model for structured output. So I need a good variable field names, and also it's better to have some description if it is required. For time, we have this scheduled item time PyIdentic model, which has start time and end time. And I'm again explaining what's the format that I want. So this description is going to be added into the prompt. Let me just show you that. So this is how the actual prompt looks like. And this is LLM's return. And it used the proper format that I asked here. And the way it did is I added the PyIdentic model schema into this prompt, which is in this metadata. And LLM is using that information for function calling. That's how LangChain's structure output is implemented. Here we have a time field that has end time, which is string, and it has a description here. So LLM reads this and fill it accordingly. Lastly, we have schedule item type. We have a bunch of types, but I want to emphasize there is a remove type as well. And I'm going to explain in the fill schedule loop very soon. Okay, so this 900 code is what's implementing this workflow. And it has a lot of prompts, a lot of extra codes that is for streaming. So I can't explain everything here. So I'm going to focus on 3 nodes. The first one is fill terminal transportation schedule. So this node is basically this one. So we're adding terminal schedule item from accommodation from terminal to accommodation, or accommodation to terminal. And in order to do that, we need to do some search. We need to know how to get to accommodation from the terminal and vice versa. So I'm using Perplexity for here. So I'm using Perplexity and I'm giving trip information and I'm asking it to find shortest path, various methods, and so on. And I'm giving some example format, an example information that I want to get. And once the Perplexity returns its response, I'm using Anthropic Sonnet 3.5 and create the schedule item. So this is for that prompt. I'm using the information above, create 2 transport type schedule items, one for arrival and one for departure. So I'm invoking this LangGraph chain with this prompt. And we have this Perplexity chat model first. So Perplexity chat model will use this prompt and return its search result. And I'm getting the search result as a string. And I'm concatenating it with prompt for chat model. Prompt for chat model. So this one will be concatenated with the search result. And I'm using this with structure output method from LangChain. So if the result will be this format. And this one has actions field, which is a list of scheduled action. And each scheduled action has reasoning field for reasoning and schedule item, which is basically the schedule items, the PyIdentic model. that we looked at here, right? I want to look at three things in this node. First, look at how I curated the prompt. So this prompt is for search. We're searching the transportation option between accommodation and terminal. And I'm only using information that is required. So we had many other state variables like trip budget, trip theme, startup day, fixed schedule, schedule list. I'm not using those. I'm only using accommodation location, arrival terminal, departure terminal, and time. So one takeaway is you have to discriminate it when you're curating this prompt. Don't add everything into a JSON schema, right? Only curate specific information and also make some headings so that LLM can understand what this information is about. That's the first thing. Second, here I'm explaining the format that the LLM should follow. And I initially had this one, etc. or others field. But I recommend you to be specific and don't be lazy when you're making this format. Because if you have these ambiguous and, you know, the term that can hold everything, you're going to end up having some information that you didn't want it. So this is the example that this is the example when I use the etc. field. It returned all the information that I asked, but it added a bunch of information in etc. field. So I don't have control over it. So if you give some room for LLM to add extra information, it's going to use that field and you would have unwanted information. So when you give structure or format for the model to follow, you have to be exhaustive. You should not be lazy and explain what are the information, what are the information you need. So that's the second one. The third one is ID. So here, I'm programmatically reassigning IDs for schedule item. So if you remember, schedule item has ID field, and I'm passing this piloting model to LLM, so LLM will fill this ID field as well. But here I didn't give LLM what schedules I already have. And the schedules that I already have already have IDs on it. So it's going to overlap when LLM returns its own schedule items. For example, this is a prompt that I went into the LLM. I'm giving the search result, and I'm asking, using the information above, create 2 transport type schedule items. And then it created this schedule items, which has ID 1 and ID 2. But I already had 2 schedule items that has ID 1 and 2, which is the terminal schedule that I hard coded in the prompt. I mean, if you remember, before this node, we already had this node, right? So in this trip schedule timetable, we already had these 2 schedule items, and these schedule items had ID 1 and 2. So when LLM returned new 2 items, the transport schedule, and it has ID 1 and 2, it's gonna crash with these things. I could have prompted LLM to use ID 3, 4, but it's better to programmatically check the ID and reassign it. based on the length of schedule list. So that's the third takeaway. Okay, so let's move on to the next node. The next node is generate search queries loop. So this node is this loop. And I'm not going to focus on how I implemented this loop. It's quite complicated. I recommend you to look at my code. But I'm only going to show you the importance of order of fields. So what I'm doing here is this is basically this reflect node. So LLM already created maybe a few search queries, and I'm asking LLM to reflect and validate each search query meets the criteria. And how I'm doing is I'm using this Python model. So in this action is a generate search query action, and this has query ID, rationale, type, new query value. So basically, the LLM will go through all the search queries and create this actions list. It will go all the queries and explain why you want to do this action. And there are four actions: add, remove, modify, skip. So looking at all the search queries, and LLM decides, should I skip it because it's okay, or should I remove this, modify this, or should I add a new one? So LLM deciding that. And the thing that I pointed out here is this one, the order of this. So I have this after this. This is current queries good enough? I have to put this after this because this field is basically validating each search queries. So if you have this before this, you're basically deciding all the search queries are good enough or not, and then doing validation step. You want to validate each queries and only say true for this when all search queries pass that validation, right? So always be careful when you have this validation field. It should be at the end. And sometimes some models don't follow the order. So you can specify you have to return this field first. But I found that Claude Sonnet 3.5 was reliably following the order. So it's up to you. Okay, let's move on. So the last node is fill schedule loop. And this is really big one. I have 7 things to discuss in this node. First, when you do looping, how would you implement that loop with this LangGraph code, which is basically graph? I would do it in this way. So you first initiate and then loop it. When you initiate, you create internal state that will be used only in that loop. So this will separate concerns. And I'll show you how I did it. So here, the state is fill schedule loop state. It's not the overall state that I introduced in the beginning, right? It's a different one, but it's inherited from this overall state, but it has this extra field, which is fill schedule loop messages. Since I'm looping it, I'm going to use message type to add what I've done in the previous iteration. I don't need this state variable other than this loop. So we're in this field schedule item loop. I don't need the message state variable in this loop, right? I don't need it here nor here, right? I only need this state variable in this loop. So I'm initiating a new internal state so that we can separate concerns. Okay, second, I have many utility functions, and I have actually three utility functions, and I'm going to explain what they are. The first is convert schedule items to string. So, as I showed you, we have this list of schedule items, right? And each of the schedule item was pydantic model, which has ID type and so on. So how are you going to pass this to LLM? You can do it as you can just like dump it into JSON string and hope the LLM can understand it. But I said you should make prompt more ergonomic. So here's what I did. I'll show you the actual prompt that went into this model. And as you can see, it's very nicely formatted. It has this heading. It has this markdown bullet point syntax. It has a nice time, formatted time. I'm not repeating the date even here because it's obvious that it started from 5 p.m. and it ends at 5:30. It's going to be the same day, right? So I'm removing that date time for the end time. And I'm not adding description and suggestions here. And also I'm creating this empty slots. I'm showing LLM which part of the schedule is empty. Otherwise, LLM should figure out by looking at all this thing and, okay, here there's some empty slot. Here there's empty slot. It's very error prone. So why don't you create a utility function that just return this string so that LLM can focus well. Or LLM can just don't waste its attention figuring out which slot is empty. Okay, so here I'm using this utility function, convert schedule item to string. And I'm passing scheduled list, the state variable, and I have different parameters. So include IDs. No, we don't need IDs here. Include description, suggestion. No, we don't need them because we're filling new schedule items, not modifying or removing. Okay, so those are utility functions. And then I put extra effort to make the prompt really nice and easy for LLM to understand. Okay, we have two more things to discuss. The first one is criteria. So, as I said, fill schedule loop is a reflection node. It's checking if the schedule items the LLM added just in this iteration, meets the criteria that I've provided. And here's how I did it. So instead of just adding schedule criteria in the prompt, um, I instead of in so okay, when you're generating the items, I just put all the criteria into the prompt like this. But when I'm validating it, I'm not putting criteria there, but I'm putting criteria in function calling. So here, I have this function calling information, and reasoning for criteria 1 has description. Think out loud if provided schedule items meet the following criteria. Fill in event in order, starting from the earliest empty slot. So, and this is criteria 1. I have 5, 6, 7 criteria. Then LLM will return each reasoning for each field. Instead of just like one paragraph that covers all the criteria on its own, I'm forcing LLM to take account all the criteria. And in order to do that, I had to create the pydantic model dynamically. So here I'm creating these fields that has criteria 1, 2, 3, 4, 5, 6, 7 that has the description of this criterion. And then I'm adding that into, I'm creating that pydantic model, and then use that pydantic model in this structured output. Okay, last thing that I wanted to touch on, remove messages. So in order to understand this, first you have to, so before explaining this, I'll show you how I'm doing this. So this was a reflection, and let's see what's the input, the prompt looks like. So, so this one, you can ignore that. Sometimes class 1 and 3.5 returns an empty string, empty dictionary. So I'm just adding this, trying it. So system prompts at your trip planner. This is a user information, and you search this on the internet. And the first human message is fill the schedule with the brief best schedule item, and here's the current schedule. Okay, and these are an empty slot, and these are important rules, right? And this is the AI generated these prompt, these schedule items. Okay, so LLM generated these schedule items in the fill schedule loop. So here we have fill schedule items and reflect, right? After this node, the AI will generate schedule items, and that is this one. It generated 3 schedule items, and it has ID and all information it has. And I'm asking, verify if schedule item you just returned meet the criteria. And I return this. And my question is, do we need to keep all of these messages when we do this the next time? So what I mean is, we're looping through this many, many times until you fill all schedules, all empty slots. And do you need to keep all the messages of generating schedule item, modifying, generating schedule item, reflecting, all the steps in the message history? No, right? When you are reflecting or generating, you just need the recent schedules, current schedule timetable, and the recent generation by the LLM. You don't need the before iteration, or you don't need the first iteration, right? So what I'm doing is I'm removing the messages. So I'm not sure if it makes sense for you, but here's the takeaway. In the loop, you can use message as the state variable that contains all the information you need in that loop. But don't passively put everything or keep everything in that message. Read the prompt that actually went into the LLM and think, do I need this information? In most cases, you can get rid of it and create a new succinct way of way to represent the current state. So that's a takeaway. When you're using message, don't clutter the message history with irrelevant information. Always kind of summarization or re-representation. Use some program, write some program that summarize all the interactions and keep it in a one single few message item. Okay, so there were the three nodes that I wanted to touch on. I'm not sure if I explained well enough, but I'll share my code base so you can take a look on your own pace. To sum up, I tried my best to optimize the prompt so that the LLM can understand it better. For example, I curated only relevant informations, and I also formatted state variables so that the LLM can understand it better. I removed redundant information, for example, the date, and I also created new information, for example, empty slots, so that the LLM don't have to calculate which slots are empty. And I also reassigned IDs as a guardrail because LLMs sometimes make mistakes. And sometimes I'm not even giving LLM enough information. Lastly, for validation, I used function calling and added the description for each field as a criteria. In other words, I was forcing LLM to check each part of the criteria one by one. Okay, so now I'm going to propose the Agile manifesto for flow engineering. This is a first draft, and I encourage you to join the discussion and share your experience, share your objections, or any kind of suggestions. So the first principle is I simulate with humans before building. As we walk through the 7 steps to create the workflow for trip planning, you can have that 7 steps in your organization with engineers, product managers, experts, or stakeholders. Having this step would take up to 2 to 3 hours, but it would save a lot of time. For example, you might presuppose that LLM can have good judgment or LLM has a working memory. By having these 7 steps, simulating with our own, we can have a better starting point. Second principle is I always account for the LLM's lack of good judgment and working memory. I extract judgment-based decisions and replace them with criteria or decision tree. I objectify criteria as much as possible. So I make criteria more objective even if the criteria is fundamentally subjective. I manage information that LLM need with state variables in a well-organized structure with proper update rules. Third principle is I use LLMs only when it is necessary. So LLMs is great technology, but you don't have to use it all the time. Some tasks that are repetitive or requires hard math or algorithm, then you can just hard code it with Python code. Principle number 4, I think bigger, tweaking the specification of input and output to design flows more efficient. If you're in an organization, you have to talk to product manager, UX designers, and think, how can we streamline the input and output so that we can make the flow more efficient? For example, instead of having complicated input step, you can just have a simple form. Or you can only focus on majority output instead of covering all the edge cases. Principle number 5, I respect LLMs and listen to them. And here's what I mean. Instead of blaming LLM for its mistakes, I read all prompts and outputs carefully to understand them better. I design prompts more ergonomic so that it can be more intuitive for the models. I design guardrails to make up their mistakes. I try my best to analyze LLM's decision to understand their reasoning. So, when I think LLM as a machine, I tend to be more frustrated or I tend to more blame them. But when I think LLMs as a human, I have more room to understand them or listen to them, like we as a human always do with each other. LLMs are already good at doing the tasks, but only when you provide proper context. And if you blame LLM and think it's LLM fault, that's why it's not working, then you're going to lose that opportunity to use the full capacity of LLMs. But if you try to listen to them and respect them, believe in their capability, then you can get more out of it. So I think this is very important trait for both flow engineers and prompt engineers. This is not the end. There should be more principles, and also we have to refine these 5 principles. I'm open to all kind of discussions, objections, and suggestions. Please share your opinion in the channel that I shared in the first comment. So that's everything that I prepared. Thank you so much for watching my video.